I mentioned last time that I'd added an extra page into this just to divide up this part 4 into 2 parts. Last year, if you've looked at any of the recordings, there was one long recording. Of course, there's no reason that you would have looked at that because you're actually physically here. And so we talked last time about retardation and attenuation. Actually, I made some paste notes in terms of what I wanted to recap. Sometimes it's better if I think about what we're going to talk about. And you'll recall, it might be easier just to scroll back through some examples. And this was kind of the key issue. And the key issue, I think, is that if you look at cocktails of different species, so in other words, if you put in at the source location at time t equals 0 days, a dissolved mixture of tetrachloroethylene, carbon tetrachloride, and a salt, road salt, then if you look 2 years later, then they will have traveled different distances. And they'll travel different distances because they are retarded, because they're sorbed onto the substrate that they flow past. And that presumably seems like an important thing, right? If you're expecting that based on the advective velocity of the fluid that your tetrachloroethylene plume should have been here, and it's actually only here, then that's something you might want to know. And we also might be curious as to what the peak concentrations are that are here. We'd expect that if it's sorbed, heavily sorbed, then that would actually reduce the peak concentration that you'd have. And so that is one effect that we can see would have a real influence on our understanding of transport. We talked about how we would modify the advection dispersion equation to accommodate that. It's interesting how sometimes my handwriting is actually decent. Vulnerability, oh my God. Keeps on coming up last couple of days. Sounds interesting. Are you trying to break into my computer? So you know what most of these terms are, but this important term is this retardation coefficient. And we know that retardation is a number equal to or larger than 1. And it's given by a simple expression, which is 1 for when there's no sorption, plus the bulk density of the aquifer, the volumetric moisture content, and so the maximum value of the volumetric moisture content is equal to the porosity. So porosity is not a bad estimate for that. And this other important parameter, this is excellent handwriting, I have to say, is this KD value. So KD is, I'll do it over here, a distribution coefficient. I guess I just have to take time to write. And that really, as we said last time, is actually, it's the ratio of the sorbed concentration on the solid to the aqueous concentration. We'll draw the diagram that does that. It's really the isotherm. And so all of this behavior is defined in terms of this parameter, K sub D. We can pretty easily get KD, we could do it in the lab by just doing the experiment we talked about, which would allow us to get it. We talked about this parameter being pretty well tightly constrained. Bulk density, 2,000 kilograms per cubic meter of an aquifer, and porosities 0 to 30%, 0.3, something of that order. Or we could actually get it from a field test, because the retardation in a physical sense is also equal to the velocity, the advective velocity of the conservative species divided by the advective velocity of the non-conservative species. And since velocity is length over time, and we're taking a snapshot here at the same time, these just turn out to be the length traveled by the conservative species divided by the length traveled by the non-conservative species. And we did that calculation last time. And that's it. And so we're trying to be able to understand exactly how this chromatographic separation evolves. So this is no different. I don't know if you still do it in high school, the experiment where you take filter paper and you dip it into a solution, maybe chlorophyll, and it separates the chemicals as it goes up. So it's chromatographic separation. It's really exactly the same process that's going on here, except it's in an aquifer, and instead of the filter paper being the medium which wicks this stuff and pulls that some out into solution, it's actually the aquifer that does it. And so that's what our interest is, in being able to do that. Okay. And so in this case we can just get this, each of these lengths, of course. In this particular case, this was equal to 57 meters divided by whatever these other components were. So 23.5. Oops. And so that's kind of a potted view of what we talked about last time. And so we might be interested, so certainly we can get this retardation coefficient. If we get the retardation coefficient and we know what these other parameters are, we can get a distribution coefficient from field data. And so that probably is the most accurate because it satisfies the fact that it's sampled a big portion of the aquifer. It's traveled a representative distance downstream, and it's under gradients which are relevant at field behavior. And so it might be the best way we can get it. But we might not always have the luxury of having a contaminated site where we can do that. And so our interest now is in being able to say something about what predictors we might be able to get that would predict sorption. So in other words, is there a way that we can get this distribution coefficient that we want to use to be able to get retardation? Because if we have this distribution coefficient, then we have the ability to be able to look at how far a plume has traveled at a given time. So it's a key parameter that we'd like to get. So the question is, can we do this painlessly just by using some recipes? And it turns out there are a couple of ways to do it, using the propensity of different solvents to partition into water. And the second one is looking at their relative solubility. So these are two ways to be able to calculate what this KD value is if we don't have any other data. And so that would tell us something about how, as we looked at this site, I was just going to draw a, so in other words, as we talked about maybe as you go downstream, and this is length, and this is concentration. And it's not so relevant for this constant concentration example. But if you have one which is where this length is equal to, in an approximate way, right? We said this length is equal to velocity times time divided by retardation coefficient. If r is equal to 1, then it's just whatever it is. But if it's retarded, then we said that it would be to have two characteristics. This would be r is equal to 2, roughly. This is r is equal to 1. In other words, conservative. And this one is non-conservative. And so the two features. One is it delays behind it, and the other one is that it self-sharpens the front. However, you could imagine that if you looked at the same case for a plume that was traveling down gradient and was a spike, a delta input, then downstream it might look like this, where it's traveled this same length here. But you can imagine that if it's sorbing onto the solid, then it's actually net removing material from as it goes downstream. So you could imagine that the retarded case, so R equals 2 versus retardation equals 1, the concentrations would be lower because some of it is attached to the solid aquifer which has gone through. And so we might want to be able to figure out exactly what those concentrations were. And to do that, we can use the same expressions we've used for these advection dispersion equation solutions, but all we need to do is be able to figure out what are the initial concentrations. Because those define, if you have 4 components, you'd have a concentration of carbon tetrachloride, you'd have a different concentration of tetrachloroethylene, different concentration of the chloride ion, because they start off at different concentrations because they're competing for places to be dissolved in water, and also they're being retarded at different rates. And so we'd like to know what the concentrations are. And to do that, we need to use Raoult's law, which you might have seen in other areas. Probably have. If we know that, if we know what concentrations are, then we can use these simple models to be able to see how long it takes to clean up some of these messes. And we can also use it to be able to assay exactly how much mass in place might be present in one particular location. We know how to do it for sure when it's non-sorbing. You just take the concentration of the component in the water. You calculate the total volume or mass of water within the plume, and that gives you the total mass. But if a portion of it is sorbed onto the aquifer, then that presumably would underestimate the total amount of mass in place. So those are the three things that we'd like to do today. And so the first is this. So how do we calculate what KD is to be able to calculate what retardation coefficient is? It's important because the solubilities of these are relatively low. So 800 parts per million for carbon tetrachloride, which is one that we've messed around with. But the drinking water limits are, of course, even much lower. So a factor of 100 smaller, and a factor of 100,000 smaller. This is in parts per million. This is in parts per billion. And so even though they're very small concentrations, they're actually much bigger than the drinking water limits. So the one way that we can try and get values of distribution coefficient is to realize that these organic components or compounds are hydrophobic. They hate being in water, and they'll do anything they can to get out of water. And anything they can do to get out of water could be to attach themselves onto the quartz of the aquifer and sorb onto the surface. Or it could be, if there's organic carbon in the aquifer, which is a hugely attractive location for them, that they'd sorb directly onto the organic carbon. And so the rules that we'll talk about only work if the fraction of organic carbon is greater than about 1,000th by weight in the aquifer. And the reason for that is that the coefficients that we'll calculate basically say how the solutes will sorb onto organic carbon. And then if we know how much organic carbon is in the aquifer, by doing a very simple test, right? You take a piece of aquifer, you weigh it, you incinerate it, the carbon off gases, and you then look at it the weight again, so you have the fraction of organic carbon. So it's a very easy experiment to run, test to run. If the amount of carbon in there is very small, then the method that we'll use basically assumes that the stuff doesn't sorb onto anything else. And in reality, it does sorb onto the grains, onto the quartz and the clays in the system. And so if we're ignoring the fact that it sorbs onto those grains and that the organic carbon is very low, presumably the value for sorption that we'll get will completely underestimate the amount which is sorbed. And so we'll see what that is. And so there are two binary, or a threshold, where you can apply the techniques that we'll talk about today. One is when organic carbon is high enough, bigger than 0.1%, and we can't do it when it's too small. And we'll discuss why that is. This is by weight percent. Which is probably important because carbon is typically much lighter than quartz, so it's important. And I guess that's defined up here. So it's weight of organic carbon divided by the bulk weight of the aquifer you have. And we can define the organic carbon partition coefficient as this expression. Actually, it's probably easier, more logical to write out the fact that we'd like to figure out this distribution coefficient, and the distribution coefficient is just the product of this fraction of organic carbon multiplied by the organic carbon partition coefficient. Don't know if it's carbon partition coefficient. And so this is a fundamental expression. So in other words, if we can measure how much organic carbon exists in the aquifer, if we can calculate what this kind of standard parameter is for the particular solvent that we have dissolved in water, then immediately we have this. So that's it. So just have to be wary of the limits. And it's the recipe. The recipe is that we can get this organic carbon partition coefficient in one of two ways, just by empirical relationships which link it with other easily measurable things for different solvents. The first is to get it from knowing the magnitude of the octanol water partition coefficient. And so in other words, how much octanol partitions into water when you dissolve it, what the equilibrium coefficient of that is. And the other way of doing it is to relate it to direct, which is perhaps easier because this is often the parameter we have. This is the solubility of the component in groundwater. And so we already talked today that the solubility, the maximum concentration that carbon tetrachloride can be in water is 805 milligrams per liter. And so those are documented. And so this is typically a pretty easy number to have. And so if we know what the rest of these coefficients are, then we can get this from either one of these two roots. And if we have it, then, and we know the fraction of organic carbon, then we have what we want. And I guess if we have what we want, we know that retardation is equal to 1 plus density of the aquifer, volumetric moisture content, KD. So that's it. We have to be careful with units because these aren't dimensionally homogeneous expressions. They are unit sensitive or unit specific, and so we have to be aware of that. So these are slightly horrible slides, perhaps even a bit more horrible than my other slides, but they come out of Feder, so you can go back to that if you decided to make a donation to his retirement fund by buying his book. That's a good book. I think I wouldn't suggest it. And so there are, if you look in Feder, you'll find out that there are a variety of relationships that can be used to calculate the magnitude of this organic carbon partition coefficient as a function of solubility for different compounds. And these T13, 14 through to 17 refer to a number of calculations done in Feder. But basically, if we want to calculate the organic carbon partition coefficient for ethylbenzene, which has a molecular weight of 165.82 grams per mole, then what we need is the solubility of it, because the solubility goes in here. The solubility has to be in milligrams per liter. So that's everything there. So they are unit specific. So if we know that the solubility of ethylbenzene is 140, take the log of this. Is equal to 2.15, I think. This here. Has to be in milligrams per liter. If we know what the log of the solubility is, and we put it in here, then we have this expression here, constant solubility, or log solubility, and that comes out to be 2.46, which is the log of this organic carbon partition coefficient. And if we 10 to the x this, raise this number to the 10 to the x, then we end up with the value of this. So in other words, we calculate what this is. So 10 to the 2.46 must be of the order, it's just slightly shy of this is this. This is this number here. And the units that go in have to be milligrams per liter. The units that come out have to be milliliters per gram, or liters per kilogram. And so this is the magnitude of KOC in specific units. And if we have the value for KOC, and then we know what the fraction of organic carbon is, immediately we have a distribution coefficient. If you have a distribution coefficient, immediately we know how strongly retarding the species will be in the aquifer. So that's just using solubility. So the other way, no particular reason to use solubility, but a whole host of different solvents are here, so you can do it for any one of them. So this is the 2.46 here, and the actual KOC value is 288 liters per kilogram. If you want to do the same estimate using this magnitudes of octanol water partition coefficients, again, it is a recipe. You need there are a whole bunch of these different relationships. Have to pick one of them, which takes the magnitude of this octanol water partition coefficient. If you can't read this, it's KOC is equal to 0.63 KOW. So we need this parameter here. And here we have just some tabulated values for the value of log KOW equals 2.13. If you 10 to the x, 2.13, so if this is 2.13 that goes in here, you'll find that you get 135. 2 would be 100, right? Just 10 to the power 2 is 100, so 2.13 is slightly larger than this. This gives us the magnitude of the octanol water partition coefficient. If we know what this is, we can substitute it back into this expression up here, just using this equation here. And if you substitute 135 into this, we end up with this magnitude of 84.98. And if you wanted to, we could take logs of that, which would give us the organic carbon partition coefficient, which is just what is tabulated here. And it turns out that the number is wrong in Fetter's book. It should be 1.92. That's neither here nor there. The real number we want is this 84.98. This is a 4. And similar to in magnitude, same units as this, it's going to be in liters per kilogram or milliliters per gram. So just a thousandth of dividing top and bottom by thousandth. And so if we have each of those, they're numbers that we can use to be able to put into this. So all we've done is, by some recipe, know what this fundamental property is as a function of the individual solvent, or know what its solubility is. If we know that, we have enough to get this value here. If we have this value here, we have enough to get this. And if we have this, we have retardation. And this tells us everything we want to know about how fast downwind, downstream the component will travel. Okay, so let's look at what that means for us when we look at some of the things that we've tested already. So the first site that we looked at today, which we looked at last time as well, was the Borden site, where we had tetrachloroethylene and carbon tet and tetrachloride and chloride traveling together. It turns out that the fraction of organic carbon at Borden is low. So it's lower than the limits that we talked about. We said it should be maybe only as small as 1%. for FOC, and it turns out that it's almost a tenth of that. So what we could do is we could try using the approach we just tried for Borden, even though we know it's perhaps going to be wrong, and see if it predicts in the way that we think it would do. Would it underpredict or overpredict? So that's, I guess that's the question you might ask yourself. Do we think it's going to underpredict the magnitude of retardation at Borden, or do you think it would overpredict? Think about that if you have your own idea. And so we're going to use this 0.02%. We're going to calculate this for carbon tetrachloride. We know that the solubility of carbon tet is 805 milligrams per liter. We can substitute it in here, take the log of that. It's going to be something like 2.9. It's going to be less than 3, because 1,000 would be 10 to the 3. 10 to the 2 is 100, so it's going to be less than 10 to the 3, so it's actually 2.9. Plug and chug with everything in this, we end up with the log of this of 2.04. If we 10 to the x, 2.04. So in other words, this is our value of x, which we use. Then we end up with a value of not log KOC, but KOC being equal to 110 milliliters per gram. And if we multiply 110 milliliters per gram by, bless you, fraction of organic carbon and KOC, these are the two components, this and this, we end up with a distribution coefficient of 0.02 milliliters per gram. So again, being a little bit careful to, sometimes not so careful, to be straight with the units we use. We didn't dwell on this. Well, actually, we did the calculation, but we didn't spend much time on it. If you remember, the calculation we did was we took these two different lengths that the plume had traveled, unretarded, and for carbon tet it was 23.5. If we looked at the ratio of those for carbon tetrachloride, the retardation was 2.4 times slower than the unretarded plume. And if we use those, we could just rearrange the retardation coefficient to get KD. So these two equations are just the same, just rearranged. And if we got a KD value, the KD value we got was 0.213 milliliters per gram. So 0.213 in this particular case, which we'd expect to be reality because it's measured in situ at the right scales and the right gradients. And when we, when we did it for the incorrect application, I guess, of our fraction of organic carbon, we got a KD which is basically an order of magnitude lower. And so then the question is, why is that? Is it in the right direction? Should it be lower or higher? And so I think you'd expect it to be lower, right? Because what we're assuming is that if we only have 2% of 0.2 200ths of 1% of carbon, we're below the threshold where we should apply it. The assumptions of the model that allow us to be able to use this approximation are that all of the sorption goes on only in organic carbon. And so if there is no organic carbon in there, then there can be no sorption. And so the magnitude of sorption or the distribution coefficient you'd expect to calculate would be much lower than the real one. And so it works out to be the right way around. Perfectly logical. So you have to be careful about how you apply it. And so we applied it in a stupid way when we are basically only 5 times below the threshold, I suppose. But it doesn't work. It doesn't work for that reason. Okay. So what are typical magnitudes of these retardation factors? So you might not be able to see this very well, like many of these notes. But magnitudes of these vary from 6, if you can read that, to 2 to 3, to 33, depending on the individual compounds. So these are a variety of different hazardous waste sites, Superfund sites, with different compounds here. Same aquifer, but different compounds. So you expect a spread of these. And these would rank, I guess, in terms of magnitudes of the octanol water organic carbon partition coefficients calculated from solubility or otherwise. And so I suppose they would be ranked in terms of the magnitudes of those parameters. Some of them are close to 1, in some cases. Some of them are of the order of 10, up to 10. So anyway, you see a range of these things. So 1 is obviously the bottom limit for these, and the upper limit seems to be of the order of a few tens, right? 23 here for carbon tet, 33 here. Those are the highest ones there. So just for a variety of sites, which we'll look at a little later. So you get some appreciation of the kinds of magnitudes. The ones we got when we looked at Borden were a factor of 4 for tetrachloroethylene and a factor of 2 for carbon tet. So if you'd want to be able to calculate, and you're going to do this, so I guess remember this. So you've done some work already on this Smithville site, this cleanup site. And you know that at Smithville there is a cocktail of things that leaked into the groundwater. So it was a place where electrical transformers went to die, copper wiring with oils around them with PCBs in them. PCBs because they are thermally very stable, so as they get hot they don't degrade. And they were broken open. The stuff was put in a lagoon that was lined ostensibly but leaked while the other scrap was taken away. And this mixture of multiple components, which I'm not sure you've done really an assignment with, but the proportions are of TCE, trichloroethylene, trichlorobenzene, PCBs, and mineral oils are in these percentages. And so the question then is, if you have this lagoon upstream somewhere that contains these components, which has leaked into the groundwater at as free phase, then when you look at the source region where this might exist, as these little ledges with ganglia hanging off on the other side and dribbling down, and if this was in water that happens to have sand in it, could be in a beaker, but you fill the beaker with sand. I guess the question is, what is the concentration of TCE? What is the concentration of the PCBs? What else was it? Carbon TCE, TCB, and the concentration of trichlorobenzene. And so, what are those concentrations? And that's important because all of our calculations using these advection diffusion solutions rely on the fact of knowing the concentration upstream to be able to project what the concentration is downstream. So that's the first step. And so we know, for instance, that the solubility of TCE is something of the order of 1,000 milligrams per liter, 1,000 ppm. But if you put this in water, just like sorbing stuff onto solid, it has to compete for these solubility sites in the water as it's dissolved. And some of those solubility sites might be taken up by the other components. And so we want to be able to figure out exactly what the initial equilibrium concentrations would be. If it's 100% TCE, then this would be the maximum concentration. If it's 2%, then that doesn't follow. And that's because all these different components are competing for different solubility sites in the water. And so to do that, we just use Raoult's law. And Raoult's law says that the effective solubility of a component, this effective solubility, is equal to its pure phase solubility multiplied by its mole fraction. So that's it. So it's not just weight percent, it's just mole fraction. And so if you know what the weight percents are of the free products together in this DNAPL, it is a DNAPL, then immediately, if you know the concentrations, maximum solubility links, this is very easy to calculate. So the only trick, I guess, is being able to figure out what the mole fractions are, and that's not very difficult. And so to do that, we can do that for Smithville, this one site, again in Ontario, not so close to Borden, a couple of hours away, but not so far away either. And so these are actually the proportions that are present within the free phase contaminating fluid within this. 2% TCE, 10% TCB, 50% PCBs, and 38% mineral oils. If we know the formula weights for each of those, which we know well for some of them and less well for others, then we can calculate as a function of those formula weights exactly what the mole fraction is. So you take the percentage of the component by weight and divide through by the molecular weight, 131, and we get a mole fraction, how many moles basically in the cocktail. If we take 10% divided by 181, we'd end up with this. Etc. So this is the number of moles of TCB. These are the number of moles of PCBs and of mineral oils. If we sum them all up, this is the number we get. So these are the number of moles per 100 grams. Because this is percent is just 2 grams would be 2% of 100 grams. I guess that's what we're doing there. Since this is the total mole fraction, if you divide the number of moles by the total number of moles, which is this gives you the fraction. And so for the lighter fractions, it gives you slightly more than the weight percent. For the heavier fractions, it gives you slightly less than the weight percent. So it doesn't change it very much. They're still roughly in the same rankings, but actually it does. It changes it from 50% to 33%. And so now if you multiply this 0.335 times whatever the solubility is for PCBs, which is 0.2, then you'd end up with whatever this number is, which is off the screen. I don't know. It will come up. Oh, it does. Look at that. So in other words, well, I thought I was doing a good job there. Okay. So in other words, 0.022 times 1060 should be 23 point something. So 0.022%, or 2.2% is 0.022 multiplied by the solubility, just gives you this number here, which is the effective solubility. So rather than having it in solution at 1060 parts per million, it'll actually be in solution at a maximum of 23 parts per million. Big difference, right? And so we need to be aware of what the relative proportions are upstream. And so when we're doing these calculations to look at the motion of this downstream, then the initial starting concentrations, as we start at the upstream location of this core plug, which is what we've been using to calculate our transit downstream, the initial concentrations that we have at this point for TCE would actually be 23 ppm, which is the same as milligrams per liter. Okay. Milligrams per a liter of water is a kilogram, right? So milligrams per kilogram, basically. So parts per million. All right, and so that's important. So that defines the magnitudes of the concentrations that will be present upstream. And likewise, we know what it will be for TCB. It's going to be 1.5 times something. This looks, I didn't do this calculation. Likewise for these other ones. But anyway, you're able to calculate it just by the product of these two numbers. This percentage as a fraction, obviously, not as a percentage. Okay. All right, so that's that. So I guess the other thing which we don't need to note here. So the other thing is, so if you now take a sample out of an aquifer, and for instance, if you would find that the concentrations, aqueous concentrations within that sample were, for this particular cocktail going in, were larger than 23 parts per million, say they were 100 parts per million, the conclusion that you might come to is that it can't really get to that. And so that's one way that you have for being able to say that potentially the only reason that it could be higher than the actual solubility limit would be if it's there as a free product. And so you might not necessarily be able to see the free product in the sample, but if it's higher than the solubility limit, the maximum that it can hold in water, it would suggest that you're entraining free product into your sample fluids that you're taking to the lab, and therefore free product must be present at that depth where you take the sample from, which is interesting information in itself. So that's the other use of being able to understand magnitudes of that which would be above that. I'm not going to go through this sheet here, but you could imagine that if instead of taking a water sample and assaying to figure out what the concentration is in the water sample, you took a solid soil sample by some method that we haven't talked about yet and took it to the surface and then sent it to the lab, and you found out that the equilibrium concentration in the water, in that sample, not the water, or the measured concentration was larger than an equilibrium concentration for the sample, then you could come to the same conclusion as well, right? That it's present as a free product. But you should realize that the mass that would be present in the soil sample relative to the mass that would be present in just the aqueous sample if you sucked it out would be different, right? Because some of it is sorbed onto the grains. So you'd expect that in the soil sample, if they're equivalent in terms of the volumes of the aquifer that you sampled, all the water out of a cubic centimeter of the aquifer and all of the soil and water out of a cubic centimeter of the aquifer, there would be more mass in the solid sample and liquid sample combined because some of it's sorbed onto the substrate. And so if you wanted to check whether the concentration in that sample was larger than what it should be based on the aqueous concentration to be able to see if there's free product, then the expression that you'd have to do would have to incorporate the fact that some of the mass would be attached to the solid. And the way that you index the amount that's attached onto the solid is through the KD value. And so you'd expect that the concentration in the water would in some way be indexed relative to that. So I'm not going to belabor the point, but merely to make the case that if you take samples, both either aqueous samples or a solid sample that includes the water, then you can check whether the concentrations in that are higher or lower than the maximum admissible amount, and if they're larger than the maximum admissible amount, there must be free product there. That's it. That's what I'm trying to say. Okay. So we've said something about the rate at which these things advect downstream. We've said something about what the equilibrium concentrations would be. If we know something about the concentrations that we present in these samples, then we might be able to, and actually you've done this calculation already, be able to say something about how long it would take to clean up a site by just pumping and treating it. And one way to look at this would be actually some kind of classic experiments conducted by Schwieler. And actually I'll make it bigger so you can see this thing. And it's basically an aquarium. So an aquarium you fill with sand, which is half a meter by 1.5 meters by 1/4 of a meter deep. You put a pool of TCE, a NAPL in the bottom, and you fill the rest up with sand after you have that. And then you flow water across from one side to the other. And you measure the concentration as it comes out, as it's traversed along the top of this, right? So the water's gone along the top of this and comes out and goes downstream. So the edges, the sides of the box are open. And if you change the velocity across the sample from 1 meter to 2 meters to 4.5 meters to 7 meters per day, so in other words, 1 meter a day would be that it would take a day and a half to fill one pore volume of this tank from one side to the other. And you look at the concentrations on the downstream side, then at very low velocities, it's relatively high concentrations. At very high velocities, it's relatively low concentrations. And in all cases, the concentrations that come out are really small in comparison to the maximum concentration that could be present. And so they're something of the order of, well, they're much less than 10% of the actual solubility limit. So if this is TCE, which it is, the solubility is 1060 or 1100 milligrams per liter. If it comes out at 90, then it's less than 9%, obviously. And so why is that? So part of the rationale is that in fluid going through here, it only has a very small contact area. And so if you looked at what would the profile look like? The velocity profile as you went across here, I suppose would look like this. And this would be this Darcy velocity of 1.1 meters a day. And so as this water goes across the top, it's certainly in intimate contact with the pool, but the stuff that's 10 centimeters above it, the pool has to diffuse up through here to get to that point before it can be carried out here. And of course, it's continuously being washed away from the bottom. And so the issue is that it can't diffuse fast enough to get up into the mainstream to be able to be carried away at a higher concentration than something like 10%. And so if we want to do realistic calculations for how long it would take to deplete this NAPL-filled region, then we have to have realistic magnitudes of the concentrations as a proportion of the maximum concentration that we expect to get out of it. And so in the calculation we did before, actually we did it on the board, I thought, for one of the assignments, was that we could say that we have a certain mass of contaminant in place. If we know the mass rate at which we're removing it, then if we divide one by the other, if we divide the mass by the mass rate, then we get the time taken to remove it. We did the calculation. And so the mass we should be able to calculate. What's it going to be? Mass would be something, it would be something like the volume multiplied by the porosity multiplied by the saturation, right? I think. That would be a volume and multiplied by the density of the NAPL. And the mass rate of removal would be what? It would be volumetric flow rate. So meters cubed per time multiplied by density, which is kilograms per meter cubed of the NAPL. Actually, that's it. So these removed, so this is kilograms per second. And so we know that the volumetric flow rate from Darcy's law is equal to cross-sectional area, this cross-sectional area here, multiplied by a Darcy velocity. And we know that Darcy velocity is equal to advective velocity divided by porosity. So if we have the product of advective velocity and porosity together, right? These are Darcy velocities. This is concentration, which is this, kilograms per meter cubed, and this is the area of which it occurs. So this is this area here is this. This is concentration. And the Darcy velocity is merely these two terms together, just written a different way. So mass divided by mass rate if we know some parameters, we can immediately calculate what that is, if we know what the mass is. And we did that calculation. And I won't belabor the calculation here. We know that if you know what hydraulic conductivity is, and you know what hydraulic gradient is, we should be able to calculate what advective velocities are. If we know what advective velocities are, we can use them in here to be able to calculate this expression. And if you just go through a simple calculation to look at a reasonable gradient of 1 in 100, the reasonable hydraulic conductivity for sand, and a loading of any particular, a reasonable loading, the given density of perchloroethylene, and at the maximum residual concentration in place, 30 liters in a cubic meter, then it takes hundreds of years to remove it. And the reason it takes so long is because the solubility is very small in the first place, like this. And if you reduce your solubility by a factor of 10 because of what we saw here, then you have a really small solubility. So if you're working at this effective solubility to be able to remove it, which would be this concentration, this would be the concentration that we're doing there. So this CW is actually the effective solubility, which we've chosen. So we know the maximum magnitude would be if it's in a free phase component. If it was present there competing with other solutes, then it would be lower than that from Raoult's law. And because it has this issue of mixing, then we have to reduce it by some amount. Not very scientific to just say reduce it by a factor of 10, but it's probably not too far from reality. It depends on the velocity. And so we might want to have a better way of being able to figure out exactly how we deal with this effective solubility. Seems like a bit of arm waving in terms of, well, we take the magnitude, it could be at maximum. Well, that's not a bad value because we should be reasonably assured of that. But then we just multiply it by this times 10. Why times 10? Why not 100? Why not 1? Why not 100? And so one way to attack that is to look at the geometry of dispersion around a source. And so these sources typically are waterfalls that end up on a capillary barrier and are a lens. So they're kind of disc, like dinner plates, I guess, but maybe a bit larger, certainly larger. And they would have some diameter attached to them, which we'll call the length of the pool. They have some height that's attached to them if we look at it in cross-section, which is the height of the pool. And the idea is that fluid going around this, both top and bottom, has to have anything that's present here, at the boundary of this pool, it has to physically get up here to mix. And it takes a finite time to be able to do that. And so what we could do is we could use a solution for diffusion, molecular diffusion, for how quickly stuff gets into this flow field, to figure out what the distribution of the concentrations would be around, above and below this pool. And then if we know how quickly stuff is being removed by water going above it, we can make a stab at the mass rate of removal. And we don't need to derive it, but the mass rate of removal in this particular case is this. It's equal to 4 times the coefficient of vertical dispersion. Vertical dispersion is a function of 2 things, as we know, right? Diffusion by random walk, molecular diffusion, and also by dispersion, mechanical mixing. This advective velocity is the velocity not perpendicular to this, because there is no advective velocity perpendicular to this. It's the one that's in the direction of the flow field, V sub A. And so if we know the advective velocity downstream, if we know the dispersion, guess what would we use for this? I suppose we want to use something like the length of the pool divided by 10. Right. Remember? Remember, if you wanted to be able to get a value of this transverse dispersion, maybe divided by 30, not 10, right? Remember this figure from a few times ago? Don't want to give you whiplash. this one. And this is that this magnitude of longitudinal dispersion is equal to some length scale, how long the plume is, divided by 10. This is the longitudinal dispersion. You'll recall that what we're after is the transverse dispersion going perpendicular to the flow field, and that is often equal to about the longitudinal one. It may seem that we're just pulling numbers out of the air. It's typically less than it, right? Because the longitudinal spreading is much more virulent than the lateral spreading of these plumes. So I suppose this would mean that the expression that we might want to use is not the length of the pool divided by 10, but since it's this, it's the length of the pool divided by 30. Not a number hard in stone, because you remember this big spread either side of this. This 1 over 10 parameter is just this line here. And there's a huge amount of scatter either side, but at least a ballpark, a way of being able to rationally choose something. Choose something anyway. All right, let's see if I can find my way back to where I was. So it's just a closed form solution. We want to know the magnitude of this. We've said that this is wrong because we think that this probably should be 10 times 3. Should be 30. The length of the pool, which is just this dimension, pi, the constant. The solubility, this is solubility. And so the maximum value, which should probably be 100% solubility for that component, if it's a pure cocktail or one component cocktail, and the effective porosity of this here. And so if we have all of these, solubility of the material, the porosity, the geometry of the pool, how quickly water is flowing by it to be able to get this, dispersion coefficient derived from this, we have everything we need to be able to calculate how quickly we remove it per unit area. So the units of this, you can check the units, they're in units of mass per length squared per time. So if you have a pool that in plan view looks like this is the mass that's coming out of a piece which is 1 meter by 1 meter on edge and removing itself per unit time. So this is mass per time, but it's only per unit area. Per unit area of the pool. So if the pool is 10 meters long and 10 meters wide, then you multiply this number by 100 to be able to get the mass rate of removal. To get the total mass rate of removal. The other thing we can do is that just as we did before, maybe I'll try getting both on the same screen at the same time, is that if we want to know the time taken to remove it, it's going to be equal to the mass divided by the mass rate of removal, which in this case we've called m sub a. And these also have to be per 1 meter squared pool area. Right? Since this calculation is per 1 meter pool area, then if you're going to divide it by the total mass available, then it would be the amount of mass that's available in this 1 foot by foot brick as you go through the pool. And so that's exactly what this expression is. The mass removed per square meter. What's the amount that's present in the pool? It's going to be the height of the pool. I don't know why I changed units. This is really HP. I guess I was dyslexic on that, switched it. This is HP, the height of the pool, how thick it is. The porosity of the aquifer and the saturation in the pool. So porosity times the height of the pool is what? That's the volume of the void space per unit area. The volume of the void space multiplied through by its saturation is the amount of volume which is the NAPL. And if you multiply that volume, so this is V NAPL per meter squared pool area. And if you multiply the volume of the NAPL times density NAPL, you equal the mass of NAPL. So that's all this expression is. So the numerator is just the mass of NAPL. So the volume of the voids multiplied by saturation is the volume of the NAPL, multiplied by the density of the NAPL is the mass of the NAPL. And if you divide through by how quickly you remove it per square meter, that gives you how long it takes to get rid of it. And it's the same calculation as before. But what's different from before is that now we haven't had to come up with this arbitrary number for, let's use 10 or 100 to say what this mixing ratio is. We actually have a rational way based on how quickly it can diffuse, and that's conditioned by how quickly the stuff flows past it. So we have rational ways to do it. Okay, one more thing. The other thing that we might be interested to figure out, we've covered actually a decent amount of space. We figured out how to say something about retardation rates, how quickly it will move downstream, because we now know how to get KD values from typical solvents using either of these two methods. Got that. We know how to define the upstream concentration, which will set how concentrations will evolve downstream, because that's kind of the boundary condition. And if we have a multi-component mixture, they're all competing to get into the water, and so the concentrations will be less than their free phase dissolution concentrations. So that's good to know. So we now know that. If we know how much mass is present, we can calculate mass removal rates, and so we can calculate how long it would take, for instance, using pump and treat to be able to remove all this material. It's a long time typically because they're very low soluble. And I suppose the last thing that we might want to know, based on the fact that we have sorption happening, is how might we calculate if we have an aquifer, which we look at in plan view, which has a certain concentration of, say, carbon tet. What is the mass of carbon tet within that aquifer? And so that's kind of a straightforward answer, except if this is in aqueous form, then the mass would be equal to what? It would be equal to the volume of the plume, so V plume, times porosity. Right? The volume of the plume times the porosity gives the volume of the water. If you multiply the volume of water by the concentration of the plume, so this is mass per unit volume, then that's exactly what you'd expect to have in the aqueous phase, right? Volume of the aquifer that's contained within the plume, inside some limit of concentration, whatever it is. So the volume of the aquifer multiplied by the porosity gives you the volume of water. If you multiply the volume of water by the concentration, which is mass per unit volume, you get a mass of the amount in situ. But if it's a non-conservative solute, then that's not going to be correct, right? There's going to be more, because some of the mass will be actually sorbed onto the grains or into the organic carbon. And so if you want to calculate the total mass that's present, then we need to be able to account for that. And so this final little calculation is basically doing exactly that. It's taking the mass that's in the plume, and it's going to be the amount that's in the dissolved in water, but also the stuff that's in equilibrium in terms of being sorbed onto the grains in equilibrium with the concentration in the water around those grains. And so we've just done the calculation for the amount that's present within the aqueous in solution. Volume of the plume, the porosity, so this is the volume of water. The concentration multiplied by the volume of water gives you the mass, which is aqueous. Mass aqueous. So we want to figure out what the other part is. The other part is this. So this again is the same total volume, but the amount that would be present that's sorbed onto the grains would be the bulk density of the aquifer times its volume. So density times a volume is a mass of the aquifer, and so this is kilograms per cubic meter. This is cubic meters, so this is kilograms. And this is the mass that's sorbed per unit mass of the aquifer, by definition, right? So this is C star, the amount sorbed. And so the mass of the aquifer times the mass sorbed per unit mass of the aquifer is this. But we don't really know what C star is. But we do know that C star, by definition, is given by KD. So KD is just the distribution coefficient, which is the ratio of the amount sorbed on the solid versus the amount held in water. And we want to define this equation in terms of the amount defined in water because it's on this side of the equation, just the easiest number to use. And so if we rewrite this equation here as this, and if we substitute for this, this just becomes KD times concentration. This becomes KD times concentration for this term here. And if you put those together, what would it be? See if I can actually do this. Porosity times concentration that we'll take outside the brackets, and total volume of the aquifer. I'm going to take everything outside the bracket. So this by definition is going to be the right units of mass. So we want to rearrange it in terms of concentration, porosity, and volume in the aquifer, plus KD, concentration, density of the aquifer, times total volume. And this is equal to our total mass. And I'm guessing that this ends up being, we can just partition it. Concentration, porosity, volume of the aquifer. That's what this term is here. That's 1. Plus concentration. What else do we need to do? I guess we could multiply both top and bottom by porosity. And if we do that, and we take this term, and this term out, we're left with KD times the bulk density of the aquifer and divided by porosity. I actually was able to do it. Fantastic. And so you'll recognize this immediately. This is just equal to retardation coefficient. Kind of interesting, it works out that way. So the bottom line is that the total mass you could calculate from the same calculation we did before, just looking at the volume of the plume, the porosity of the aquifer inside the plume, and the concentration inside the plume. Because the plume is in equilibrium with the stuff that's sorbed onto the grains, then by definition, if it's non-conservative, or if it's conservative for that matter, we can use this expression. If it's conservative, then what's the value of R? 1, right? And if it's non-conservative, then R is some number greater than 1. So it's a universal expression. So it just accounts for the fact that we need to be able to accommodate for the amount that's sorbed onto the mass if we want to calculate what the total mass is. And it may just be an academic exercise, but this is kind of an interesting plot here What you see is these are some famous contaminated sites, Superfund sites. Mountain View, California, this is Palo Alto, so this is semiconductor industry. This is probably Otis Air Force Base in Cape Cod, Massachusetts. Gloucester, Ontario landfill, one of the examples we looked at, and is in Fetter. This might be the Rocky Mountain Arsenal, I'm not sure. But these little blobs that look like mistaken ink spots are actually the shapes of the plumes, and relative to this size. Big, big plumes, right? 5 kilometers. So 5 kilometers is 3 miles. And so these are big plumes and given by shape. And if you go back to these and you calculate from the magnitudes of the concentrations of these plumes, which we said are quite low because the solubility is quite low, then although the volume of the plume is very large, the amount of stuff it takes as free phase to make these plumes is actually really not very big. So, and in one of these cases, right, this is an oil drum, 45 or 55 gallon oil drum. So 0.4 of a drum can make a plume that is 5 kilometers in size, and presumably at very low concentrations because it's spread out. And so it's this idea of entropy. If you want to catch a plume, you want to do it early when everything's together. Once entropy enters into the place and it spreads out at much lower concentration, then it takes much more effort to be able to corral it and be able to catch it. And so that's kind of the end of the message. So that's really all we'll talk about in terms of mass transport. And so we've talked in great detail about how to define behavior of conservative systems. We've talked about how to calculate what retardation does and why it happens in a mechanistic way, to figure out exactly how we can represent that using the models we use for conservative transport, and from that to be able to make predictions about how much is in place, what the concentrations should be, how fast it will travel downstream. And that's the precursor to be able to say something about how we might be able to remediate things by sucking it out and how quickly we might be able to do it. So I'll leave it at that. Great, thank you. Sorry.